So I'm going to be talking about a lot about the Apache Mesos project, kind of start off a little bit with some containerization thoughts and kind of the microservices trends that are happening. But most of the presentation is going to be about Apache Mesos, and then at the end a little bit I'm going to talk about some of the work that we're doing at Mesosphere. So it's an emerging trend that I think we're all seeing that's really kind of cyclical upon itself, and that's a lot of organizations are moving to microservices, and a lot of organizations are adopting ideas behind containerization. And when I say microservices here, you know, one of the things that's really interesting about microservices is it really gets us back to building applications with a couple of really, really nice properties. One is that we can kind of focus our applications, these services, on doing one thing and doing it well, which is really the Unix philosophy. That lets us compose these things really, really nicely. It also lets us, as an organization, build applications, commit individual applications code in isolation, be able to test the individual pieces in isolation, be able to actually deploy them in isolation, roll back individual pieces in isolation. And that really captures a lot of the organizational structure that a lot of teams have, either working in a distributed way or in parallel really well. It doesn't mean that it's a free lunch. There's still quite a bit of work that you have to do as you start to move to micro-organizations, but a lot of the benefits outweigh the cons, and so most organizations are doing it. One of the things I think is pretty interesting about microservices in particular is that the service-oriented architecture, which kind of predated microservices, had a lot of these same ideas. And this is kind of the, as we always see in computer science, this is the regeneration of a lot of those ideas. So an organization that I was at that did the big shift to microservices was Twitter, where we used to run the opposite of a microservice and not a service-oriented architecture, a giant monolithic application that was written in Ruby on Rails that we affectionately dubbed the monorail. And the monorail kind of did everything from the routing, presentation, logic, pretty much everything but storage. That was the only other service that the monorail was really communicating with. And the transition that we did at Twitter was we went from this giant monolithic Rails application to a bunch of microservices that were all communicating amongst one another. A majority of these things were actually written in Scala, Java some as well. And kind of at the same time, what started to take shape at a place like Twitter, and then now that's happening in the general industry, is people started transitioning less and less from the way that they configure and manage their individual machines is with things like RPM, or when you go to launch your application using something like Git to actually pull your repo and build it. And they're moving more and more to things that have less moving parts. So just entire jars. The jar is your entire bundle that you deploy, or a tarball. The tarball is everything you need, all your dependencies. A static binary. That's my little static binary GIF. Or using things like Docker. And I think what's really interesting here is, you know, in the days of using things like RPM and Git for doing a lot of our configuration, package management, deployment, there were a lot more moving parts. So when things failed, they were hard to debug, and they failed more often because there's just more moving parts. And this movement in this containerization realm is really about less moving parts. When there's less moving parts, there's more deterministic guarantees. I think one of the things that's pretty interesting here is the static binary approach is one that doesn't get a lot of love. But for those of you that are writing in Go, obviously you get static binaries out of the box. And that's because at Google, with the way that they were actually deploying their applications, they weren't using RPM, they weren't using Git, they weren't using Docker, they were using static binaries. And so they were actually, when Go first created, they said, well, let's just make sure that we can build static binaries by default. Okay. So the interesting thing about sort of microservices containerization is that they're creating this reinforcing trend on more organizations not just using microservices and containerization, but also starting to do cluster management. So cluster management, in quotes, at Twitter in 2010 really consisted of using technologies like Puppet for doing the configuration and package management, and tools like Capistrano for doing our deployment. We actually built a tool on top of Capistrano that we called Murder, referring to a murder of crows. And it was to actually get Capistrano to scale to the number of machines that we were actually using. So there's one really, really missing important part in cluster management here, and that's why I put the words cluster management, and it was people. People were the ones that were actually writing a lot of the scripts to run Puppet, doing a lot of the operations very, very manually. And it wasn't just a few people, it was a lot of people. There were a lot of people that were doing cluster management in the early days at Twitter. So why did we have to have so many people? Basically, at Twitter, what it looked like is we'd take all our machines and we'd effectively go and we'd statically partition the machines. Humans would go and they'd statically partition and manage the clusters by saying, OK, let's take this collection of machines and let's go ahead and run MySQL on them. Let's take some other collection of machines. Let's go ahead and run Memcache. Let's take yet another section of machines. We'll go ahead and run Rails there. Finally, Cassandra and Hadoop. Right? So this is the standard thing that we were doing is we were going and we're statically partitioning, collecting our machines and saying, OK, these are the machines that are just going to be used for running these applications. And this is where, as an organization at Twitter, we started to run into a bunch of challenges and why cluster management really evolved at Twitter. So the first one was just dealing with failures. So this is actually a real email from 2010 where somebody had to reboot a machine in one of the data centers and they asked a very natural question, which is, hey, were there any production services running on this machine? So this is humans doing cluster management, dealing with failures, and then other humans actually figuring out how to get the services back up and running. OK, so what does that look like in the data center? Well, machines fail for all sorts of reasons all the time, and humans had to actually account for that. The next big challenge that we as an organization at Twitter really had to deal with was maintenance. And maintenance I really like to call planned failures, because effectively you're inducing a failure in the system. You just know exactly when that failure is going to occur, and so you can plan for it. There's a lot of maintenance that actually happens in our data centers, not just in private on-prem data centers, but also in the cloud. One of the biggest ones is actually upgrading the kernel. We all at some point need to upgrade the kernel, which means we're going to be shutting down our machines, bringing up other machines, or bringing that machine back up with an upgraded kernel. But of course, there's replacing machines, there's replacing switches, PDUs, moving regions if you're in the public cloud. There's lots of different maintenance-like events that you might be doing that can cause a lot of humans to be running around communicating with one another to try to figure out how they can actually do this. So at an organization like Twitter, folks unfortunately had the experience where they did maintenance on, say, the racks, the top of rack switches that were on the far side of this diagram, bringing down all the memcaches, and of course, that means that nobody's tweeting. OK. The last challenge that I want to address is really utilization. So for some organizations, this is not nearly as important a one, but for a bunch of organizations, especially as they start to scale to more and more machines, it becomes ever more important. So let me just grab some more water. OK. From the utilization perspective, when applications are running, they have different requirements for the needs, the computational resources that they need over the course of them actually running their applications. So when we kind of do this static partitioning and we divide the resources up amongst the different types of systems that we're trying to run, we end up getting a situation like this. So here I've just divided 100% up into a third each. So Memcache gets a third, Hadoop gets a third, and Rails gets a third. And this is now Rails using during certain parts of the day when not as many people are tweeting, there's all this free resources that potentially be used for some other application like, say, Hadoop. And Memcache kind of follows a similar cycle to something like Rails. So really what we'd like to do, and what humans end up doing is they end up going and say, OK, well, how can we optimize the number of resources that we should be allocating to these applications over either different periods of the day or different times? So we could get to something like this. So Hadoop could say scale up and use those resources, which ultimately means that we could buy less machines or run more applications. So I think what's really interesting about these challenges is less that they exist and more that to deal with these things, humans end up actually playing a big part of the process. So humans come in and they start having to plan for failure. How do we want to actually run our application so we can plan for failure? And here's another email, internal email from Twitter where I've scrubbed, again, some names. And the important part is really at the bottom where it says, someone is saying, hey, preferably this thing I'm trying to run is on different racks, switches, and power feeds that they are fully redundant. Right? So this is humans basically effectively doing scheduling of applications to try to figure out how to deal with and plan for failure, for the challenges they have in running stuff. And utilization is even harder because it's one thing to think about how we can share machines between whole machines between different applications. It's another thing to think about how we can actually share a couple of resources on an individual machine. So an individual machine can be truly multi-tenant, it can be running applications from multiple applications on the same machine at the same time. So in about 2010, at Twitter, we looked into actually getting a cluster manager, not having cluster management being done by humans, but actually having a software cluster manager. So cluster management, to me, there's really two things that really identify what cluster management is all about. And the first one is when you do cluster management via software, you start to stop treating your machines as pets, but you just treat them as cattle. They're arbitrary machines. You put a small and simple base operating system on all of them, and ultimately you end up running these containerized applications, where a containerized application might be a full-blown Docker image, or it might just be a tarball or a jar that has everything that you actually need. Okay? And the second really most important thing is that you start to automate everything you do in the data center with software and not humans. So you deal with, you let software schedule other software, you handle failures, improve utilization, manage maintenance, all that stuff, you do it with software. One of the things that I think is really interesting about cluster management is that it's not a new topic at all. It's a very old topic. There's been a lot of cluster managers that existed. Some have still been used since the early 1990s. Things like Moab, Torque, PBS, the Portable Batch Scheduling System. One of the reasons for that was that in academia, the kind of applications that were being built and run in academia were things like message passing interface, where they wanted to run that on a large number of machines, whereas the kind of applications we were running in industry tended to be some web servers, maybe some other one-off servers. And in academia, they already had hundreds of machines that they were able to work with to actually run these things. And in industry, we were kind of working with tens of machines. And ultimately, this led to a bunch of cluster management-like technologies being built in sort of the academic and the lab space around the world. And in industry, we kind of used SSH or other tools that we developed, which helped solve the problems like Puppet, Chef, Capistrano, and Ansible. But these days, what I think is interesting is that we're all converging more and more, both between academia and industry, on running similar numbers of machines. We're all running more and more and more machines. And in general, even if we're not running as many machines in industry as some government labs or supercomputers are running, we're running enough machines that it's enough of a pain in the butt to actually manage them ourselves. Now, one of the things that's especially interesting about cluster management as it was done in academia was that the clusters managers, they were really focused on batch computation. So they were really meant to make it easier to run batch computations. So what we did at Twitter was we ended up building out a new cluster manager called Apache Mesos, which is really a modern general purpose cluster manager that's not just focused on batch computation, but it's actually focused on running any kinds of distributed systems or applications, containerized workloads, whatever it is that you want to run. So what I mean by that is I mean that Mesos was designed to run these kinds of distributed systems as native applications on top of Mesos. Now, I'm not going to spend too much time in the presentation, at least not right now, talking about what it takes to run something like these systems on Mesos. But I'm going to spend a little bit of time talking about specifically the kind of system that we built on top of Mesos to run the Twitter application, which is all these different microservices. Okay, so what was particularly interesting about the Twitter application is if you kind of looked at this picture again, there was a bunch of things that we wanted to run, which were these stateless services that kind of sat in between the stateful stuff, the storage applications, and kind of some of the very, very front-end stuff. And there were tons of them, and it was growing every day because new developers in the organization were building a new microservice all the time, okay? So we introduced Mesos. So what is Mesos, kind of from 100,000 feet? So Mesos is a cluster manager. It's got a master-slave architecture. So the idea is that there's some collection of masters that run, and they manage all of the all the machines in the data center, and they run an agent process on each of the individual machines. Okay. Now, a really, really important part of Mesos that distinguishes it from other cluster managers, especially those of the past, is this idea that Mesos has this notion of things called schedulers that connect to the masters, they register with the masters, and they're the things that are responsible for actually running the jobs and the tasks in the data center. Okay, and I've got a couple of other slides later that talks a little bit about how this works. Okay, so these schedulers, though, is a really, really critical point that really differentiates it as an architectural technology from some of the other ones. Okay, so again, we're getting back to these stateless services. So what we did at Twitter was we built a very specific scheduler that we run on top of Mesos, a service scheduler. So a service scheduler that we built was really responsible for being able to orchestrate all these microservices that people were trying to run in the data center, okay? So I'm going to differentiate here now what I mean between orchestration and scheduling. So when you build something like a scheduler on top of Mesos, there's a programmatic API that piece of software uses to actually communicate with Mesos in order to run its applications, in order to run its tasks. So a service scheduler is some software which communicates with other software, Mesos, in order to actually run its applications. Above that, the service scheduler exposes a higher level API that either a human consumes or some continuous integration job consumes. And that's where somebody would say, write a specification about the kinds of jobs they want to run, and then submit that, effectively say to the service scheduler, here, orchestrate this job for me, and then it uses Mesos to actually schedule those jobs. Okay? So one of the orchestrators that I want to talk about first is one that we built at Mesosphere called Marathon. So these kind of service schedulers, they've got a couple of roles that they have to focus on, but the two that I'm gonna explicitly call out here is really, how you're gonna do your configuration and package management to actually run your application, and then what does deployment actually look like. So if you use something like Marathon on Mesos, as a developer, what you do is you go build your application and then you containerize it. So again, you either containerize it by sticking it in a tarball or using something like Docker to actually create an image, a Docker image that you can then run later. Okay? After you do that, then you have to put the bits that you want to run someplace. So you take either your tarball or your Docker image. If you're on something like AWS, you can throw it in S3. If you've got something like HDFS running or some other distributed file system, you can throw it in the distributed file system. And then, or if you're using Docker, of course, you can use the registry. Okay, so that's kind of the first step. You do configuration and package management when you're trying to run services. So the second step is then deployment. And what this looks like is that, again, the developer goes and they describe this application that they're trying to run in Marathon using a JSON specification. You write out that JSON specification, and then you submit that JSON specification to Marathon, which Marathon then uses to orchestrate the actual running of your application by communicating and scheduling jobs directly with Mesos. So in Marathon's case, there's a REST, some REST endpoints you can use. There's also a CLI. Okay, and this is just kind of a quick example of what running a Docker container via Marathon looks like. Here's the JSON spec, and it's pretty simple. You effectively are describing the container. If there are particular volumes, local volumes you'd want to get mounted in, resources you're consuming, and then finally at the bottom, the actual command that you're going to run. Okay, so one of the things that's really interesting about what we're doing at Mesosphere and the way that Mesos was actually built is that there are different ways in which you might want to orchestrate your containers, and that's a great thing. So in the same way that you can use something like Marathon to run your containers on top of Mesos, you could also use Kubernetes. So I know the Kubernetes talk was just before me, so that's great. So in that case, the way it works, again, the two things that as a developer you have to think about is how you're going to do your configuration and package management, and then what's your deployment look like. The biggest difference here is that for configuration and package management, you are just creating Docker images or soon AppC specs, and then you're writing your deployment script, also in this case in JSON, and then submitting that to Kubernetes, and then Kubernetes is communicating directly with Mesos again to schedule those tasks throughout your data center. Okay, so one of the things that's really interesting about Mesos and the way that Mesos is actually built is this idea that you could actually run multiple of these schedulers at the same time. So across the same data center, you could both be running Marathon and you could be running Kubernetes. So why on earth would you possibly want to be doing something like this? There's a bunch of reasons why you might want to do it. The people that we know that are doing it is because they've got some part of the organization that has decided they're going to be building some things using one specification language, and another part of the organization that's going to be using a different specification language. From our perspective, we kind of see it like browsers. There's Chrome, and there's Firefox, and there's Internet Explorer, I think. And if you guys want to use any different kinds of these orchestration layers on top, that's great for us. So one of the specific reasons, though, why a lot of people end up using something like Mesos here is when you actually want to run multiple of the same instances of a particular scheduler on top. So there's a bunch of reasons why organizations do this as well. In that place, Mesos ends up kind of becoming like a private cloud for your data center, either because people want very, very hard guarantees to different organizations for the individual service schedulers that they're providing on top. The other one that we've seen people do, though, as well, is just because they want to run multiple versions of it. So they'll start running one version of the system, and then they'll start running the newer version of the system, and once that one's hardened, then they can just start moving everything over to the newer version. And this way, you didn't have to go and spin up a whole new cluster to try to run the new version. You could just use whatever were available resources in the existing cluster that you'd already brought up. So from the Mesos perspective, the thing that we see more and more often, though, is less people running multiple schedulers this way, and more people running multiple schedulers this way, where the kinds of applications that they're building on top and running on top are things like, say, analytics, stateful services. And so now I'm going to go even deeper into the presentation and into how Mesos works to describe how this stuff all fits together. Okay. So we're going deeper. So I've got a couple of slides where we go deeper, and at some point we get pretty deep into how Mesos actually works. And so I hope I don't lose everybody, but I think it's really interesting stuff when it comes to the actual architecture of the system. Okay, so going deeper, multiple schedulers. So in order to actually make this work in Mesos, Mesos is built around a concept called two-level scheduling. So Mesos itself is really influenced by the multi-level scheduling ideas that existed in traditional host operating systems for things like user-level scheduling and scheduler activations. And in that way, Mesos was really designed less like a cluster manager and actually more like an operating system kernel. And that's actually why we call Mesos a distributed systems kernel or really a data center kernel. So what do I mean by that? Well, as a data center kernel, these schedulers, when they actually want to run their applications, they use the syscall-like API programmatically to actually launch their applications, to actually run whatever it is they're trying to run in the data center. So what's interesting about putting this level of indirection in between the schedulers and all the resources in the data center is, first, well, it makes it easy for us to actually run multiple distributed systems at the same time. Right? And if you think back to some of the challenges that we wanted to overcome with software, it's that software can schedule other software, software can manage software, and we can actually drive up the resource utilization in our cluster. And one of the ways in which we can do that is by having this level of indirection, which is Mesos in the data center, to be able to run multiple distributed systems at the same time and do it dynamically. Okay? So the other thing, though, that we really get by sticking this level of indirection Mesos in between the schedulers and the machines themselves is that Mesos can now start to provide common functionality primitives that, for the most part, every new distributed system that gets built ends up re-implementing. Right? And by primitives, what are the things I'm talking about? So exposing up concepts like principals, users, and roles, exposing up advanced first-level scheduling and fair sharing algorithms, enabling things like high availability to be done more easily for the distributed systems that are running on top, doing things like resource monitoring, introducing concepts like preemption and revocation, volume management, reservations. There's a whole bunch of primitives that we can actually provide. The simplest ones, honestly, are just run this task somewhere in the data center. You take care of getting this task from here to there and launching it, and when it fails, telling me when that thing is actually launched. Excuse me, has actually failed. Okay, so one of the really interesting things when we were first building Mesos was we were recognizing that pretty much everybody, when they build a new distributed system, they all end up reinventing the wheel, and we really wanted to provide from the Mesos abstraction layer a way to make it so people didn't have to reinvent the wheel, but they could build their new distributed systems directly on top. Okay, and I love this picture. I just love the idea of actually trying to use a bicycle like that. Okay, so the other thing that's really interesting about actually building your distributed systems on top of Mesos is that it can make it much easier for people to actually use your software. So what do I mean by this? Well, we're probably all familiar with stuff like this. We go and we try to use some distributed system that's been built by some organization, and it's so complicated to use, and it's so complicated to set up, and the software can't do a lot of its stuff itself because we got to set it up on each machine. If one machine goes down, we got to come in and deal with the next pieces. That we end up getting a whole industry of books about how to actually run the software. So if you can actually leverage an API and you can actually build the software directly on top, we can make it easier for people to actually run your applications in the exact same way that it's pretty easy these days to actually download an application on our desktop machines and just run it. Okay, so there's been quite a few of these kinds of distributed systems that have been built directly on top of Mesos. Spark is a big data analytics framework. Apache Aurora was actually the orchestration service scheduler that we built at Twitter that we open sourced a couple years ago. Marathon's the one I mentioned. Kronos is a distributed cron with dependencies-like scheduler. So it's very similar to cron on a single machine, except cron across your entire data center. And then there's also been a whole bunch of these frameworks that have been ported on top of Mesos. Things like Hadoop, Storm, Jenkins, and we're actively working on making a Cassandra port work really well. And then, of course, Mesos is actually being used at a bunch of these organizations that are using a handful of these different distributed systems on top. Obviously, I was chatting about Twitter. There's been other organizations as well. The one that I'll call out more recently is Apple. Apple actually recently announced that they've been using Mesos to run all of Siri on top. And they actually built a brand new distributed system on top of Mesos to manage exactly how they want to run Siri internally. Okay, going even deeper. Okay. I'll get some more water. Okay, so going even deeper. So the way Mesos actually works under the hood. So in Mesos, if you're actually building one of these distributed systems on top, the API that most people end up using is what's called a request offer API. And so the way it works is that when a scheduler wants to actually run an application, it can first make a request for resource. It can say, these are some resources I would like to use to actually be able to run my application, okay? And a request is really, it's a simplified subset of kind of a specification for what it wants to run. It's just the resources that it needs at that point in time, okay? Now, what Mesos then does is it takes all the requests in the system and it takes whatever other information that it knows about and it creates what are called offers. And offers are effectively allocations that it makes back to schedulers. So based on what some schedulers might need to run their applications, the Mesos masters, specifically the allocator in the Mesos master says, okay, great, here's some resources I can allocate to you so you can actually use these to run your applications. And of course, we're not just making a single offer, we're making many, many offers at the same time. So what the scheduler then does is it uses these offers, it uses these allocations to decide what tasks it actually wants to run. And this really is where this two-level scheduling comes in. So at the first level, Mesos is really making the allocation decisions about resources to individual frameworks. It could be the same kind of framework, just multiple instances of it. And then those frameworks, specifically the schedulers in the frameworks, are deciding what tasks they actually are going to run, what jobs they're actually going to run based on the available resources that they can use. Okay, once they pick a task that they want to run, and they say, okay, this is the task I want to run, then they'll submit that task back to Mesos and say, here's the task I want to run. And again, this is where most distributed systems end up having to build this piece in, where if they want to run some task on some other machine, they've had to build in the componentry to get the task to the other machine, have the machine take that task, and actually start to run whatever it is that it needs to run. In this case, they can just say, here's my task, run it, and go. Okay? So there's a couple different ways you can actually run tasks in Mesos. So you can just give a task with a command, an arbitrary shell command, and depending on how you've actually set up the base image across your data center, that command may or may not work. If you run a task with a command, it's pretty simple. It says, here's the task I want to run. There's, again, as I mentioned, there's an agent process on each of the machines that gets the task when it gets assigned to it, and then just launches the task. Okay, and of course, you can run multiple tasks on the same machine. You can also, though, you can launch tasks through what we call an executor in Mesos. So it's this extra level of indirection that lets you, as somebody who's trying to build a distributed system, be able to specify exactly how you want your task to actually run. So the way that works is, again, you go to launch a task, but you specify an executor. An executor is the first thing that we actually execute. And then we pass the task to the executor, and the executor can decide how it actually wants to run its tasks. And again, an executor can have multiple tasks. So the reason why this is really, really interesting is because it allows you to actually send tasks to something on an individual machine that don't require a complete fork exec. So if you wanted to, say, build a distributed system where you want to just do more things by, say, spawning threads or allocating memory, you could do something like that in this model. So we specifically wanted to build something, so if you were trying to build a sophisticated distributed system which didn't want to have to completely, say, fork exec to do a very, very small task, like, say, pull something off a queue and process it, that you could actually do something like that. Okay? So again, if you're running with executors, that you can also be on the same machine running just top-level tasks. Okay? So what we end up doing on each of the individual machines is we isolate with a container. We isolate the individual executors or tasks. Okay? So what this looks like is here, we've launched one executor. It's got one task running, one top-level task, and we've put a container around each of these different things so that they're isolated from a resource perspective from using one another's resources. And the technology that we actually use to do that is the same technology that's underlying Docker, Linux control groups, and namespaces. So before Docker existed, this is the way that we did it, and that's one of the reasons why I mentioned at the beginning, a lot of people that use Mesos in the early days, they just had tarballs or jar files, because there wasn't a whole image that they needed. They just had their bits in that form. We constructed the container around them, and then they unpacked their tarball. Okay. One of the things that's really interesting about this model, though, specifically with executors, is that since we put these containers around them, you can easily pass more tasks to the executor. And as we actually pass more tasks to the executor, we'll scale up the size of the container dynamically. So we'll actually add more resources to the container. So for those of you that are really familiar with vertical versus horizontal scaling, it actually lets you do vertical scaling directly on the machines as well as, of course, scale it to other machines. Okay. And of course, as the machines go down, we actually vertically scale the containers down. Okay, and then finally, of course, if you're not sending us a tarball or a gzip, you can send us a Docker image, and we'll just run the Docker image directly. Okay. So one of the things that comes up a lot when people really dive into the depths of how Mesos works is what does high availability actually look like in the system? So it was designed from day one to let all the different components of the system fail independently. And there's really not that many components. The core components, again, as I mentioned, are the masters and the slaves. And the one other component is Zookeeper, which we currently use for leader election. But those are the three core components you need to actually be running a Mesos cluster. So when something like a master fails, however, the scheduler will just get rerouted through Zookeeper to communicate with another master that's elected, and all the tasks that have been run, everything that's been launched will just keep running. Okay? The same thing with a scheduler. If a scheduler happens to go down, then another scheduler can be elected, and it will reconnect to the masters, and it will find out about any of its tasks that might have, say, failed while it was down. So this is actually a pretty interesting thing that we built in. When we first built in the notion of scheduler failover, we actually gave a timeout that you could specify when a scheduler first registered to decide, how long you wanted to wait to potentially fail over. And if that amount of time elapsed, then we would just clean up for you, and we would kind of kill all of your tasks under the covers. So what was really interesting about this was, The first time that we put it in place at Twitter, when we were running the Aurora service scheduler on top, I think we had like a 5-hour failover timeout, and then we had an outage that was like 4 hours and 30 minutes. And so we almost killed every single task in the cluster because we didn't have the scheduler reconnect to the master within the 5 hours, and so the failover would have been elapsed and we would have killed everything. So then after that, we said, oh, well, let's make it 24 hours. So we bumped it up to 24 hours, and then a couple weeks later, we had a failover. We couldn't get the scheduler to reconnect within about 22 hours. And after that, we just bumped it up to double max. So at this point, the way scheduler failover really works for most people in the organizations is either always keep it running, or when it first disconnects, shut down all my tasks that are running. But still, we have the functionality, and you can decide what you want to do there. So the last type of high availability that we have in the system is what we actually call slave failover. So again, we've got this agent process that's running, that's managing the slaves, and we actually have the ability to let that process that manages the tasks go away. And if that process goes away and a new one comes up, then it will re-find or it will reconnect any of the other tasks or any of the other containers or any of the other Docker containers that it's actually launched. So this was really, really critical to us because the kinds of services that people actually want to end up running in production are things like Memcache or Redis or other services where if every single time that our process died, we actually killed all the containers that were running, that would be really, really unfortunate. Now, of course, we don't want our process to die very much because we're going to make it as robust as possible. But there's one time when we're always going to be bringing down the process, and that's when we're actually doing maintenance or an upgrade of the Mesos layer itself. And so what we were running into was to the case where we would want to upgrade Mesos in the data center. And what we'd have to do is we'd have to go to a machine, we'd have to drain the tasks off of it, effectively kill the tasks, and then upgrade upgrade the machine, and then put the new binary on, and then stuff can get rescheduled on that box. Which is fine when you have a handful of machines, and when you start to get into hundreds of machines, to guarantee the SLAs that you want for when you start killing tasks and have them migrate to other machines, it can start to take days, if not weeks, if not months, to actually upgrade a cluster. So this was a pretty critical feature we put in. Okay, so I'm going to go a little bit further down the rabbit hole, but I'm going to skip ahead a little bit. Because we get pretty deep in the rabbit hole with the different Mesos features. So I'm going to skip talking about how we actually do our first level allocation, and I'm going to jump to some other higher level concepts. Okay, so we've got some other great concepts in Mesos that we've had to introduce specifically for running this stuff in production. The couple that I want to mention briefly are the first couple ones I want to mention is really resource reservations. So it's this basic concept that you can go in and you can say, you know what, for some frameworks that are running, for some schedulers that are running, I actually want to make sure that resources are guaranteed to be allocated to these frameworks, so you can feel good at night when you go to sleep and you know that if there's going to be a bunch of failures, that at least if there's this many resources will be guaranteed to different applications. So the way reservations actually work in Mesos is you can specify the reservations on the individual machines, and you can say, I want to create some pre-specified container sizes for some of the jobs that I want to run on top. So you can do that statically, which is great. What that really gives you is this notion of strong guarantees, but the unfortunate part about it is that it has to be set up by an operator when they're starting the slave for the first time, and it's actually immutable because once you set the reservations, you actually have to drain everything off if you want to change the reservations. So what we've recently introduced in Mesos is this concept of dynamic reservations, which are pretty cool. It's this basic idea that when a scheduler inside a framework is trying to run an application, and the first time that it gets resources that are allocated to it, when it goes to actually run its tasks, it can not just say launch these tasks, but it can also say reserve those resources for me so that I'm guaranteed that those resources will be reallocated to me no matter what. After the machine goes down for maintenance, after I fail, after there's a network partition for a long period of time, and eventually you shut my process down, whatever it is. So once we actually get the resources and the tasks to the individual machines, we do the reservations there. So reservations are great because they provide the nice guarantees that we all want when we're actually running in a production setting, but really at the cost of utilization. So when you end up having a big chunk of resources that are reserved for a particular organization, they might be using very little of those resources, which kind of goes against the whole idea of, well, we're using a cluster manager to actually be able to drive up resource utilization. So to deal with that, we have this other concept in Mesos that we actually call revocable resources. And the concept behind revocable resources is there's resources that can be used by different frameworks on top that can actually be taken back from the schedulers that have launched tasks with them. So this ends up introducing a really, really nice property for people that are trying to build new distributed systems, which is the way that they can think about preemption in their head is that preemption actually occurs through revocation. So we don't have the notion of priorities in the system. We don't have to guess who's a slightly higher priority and what semantics that's going to mean. It basically means that if you're using resources that are either reserved to you or are not marked as revocable, we're not going to take them from you. And if you're using resources that are revocable, it's highly likely that your task will be preempted to get the resources back. Okay. So one of the really, really cool things that we're actually working on with revocable resources right now is oversubscription. So what ends up happening in a lot of these organizations is they start running their tasks and users come in and they say, my task requires 8 CPUs and 8 gigs of RAM, and it uses 2 CPUs and 2 gigs of RAM. And now we've got all these resources that have been allocated but are actually not being used. So what we can do is we can take that remaining 6 CPUs and 6 gigs of RAM and we can offer them out to other things that are trying to run in the data center as revocable. They can use those resources, and of course, if that first application that was trying to use all 8 CPUs and 8 gigs of RAM scales up, then it'll actually get the resources back. Okay. So again, excuse me. This revocation guarantee that we really provide, though, which is that the task will not be killed unless I'm using revocable resources, it's tough to always provide that. One of the trickiest places when it's tough to provide that is when we might want to say defrag the cluster, because the way that stuff has gotten scheduled over time, it leads to a less useful utilization than if we could actually pack some things together and shut some machines down, or specifically when we want to actually do maintenance. So some of the last primitives that we've been introducing into Mesos recently are primitives for actually doing deallocation so that we can introduce maintenance as a software concept in the system. So one way in which we can actually do maintenance is we can, again, go around and we can kill machines or shut down machines or drain tasks from machines, and then they won't know about it. They'll just think that there was a failure, and then we'll go from there. But we can actually do better. So we got this really interesting concept in Mesos that we call an inverse offer, where an offer is an allocation of resources that's made to you. An inverse offer is a deallocation of resources where we say, hey, we'd like these resources back. Specifically, we'd like these resources back at this point in time and for this period of time, because say we're going to shut down the machine during that period, and so you can't run any tasks on it. Okay, so that's pretty cool. We can send out an inverse offer, and then the framework can say, great, yep, I acknowledge that you're going to take my resources away, and I'll shut down my resources. So that lets us introduce something like maintenance in a really programmatic way. So we start off by sending out inverse offers. Then we actually, once we've sent out all the inverse offers, we can continue to send out other allocations, but just mark the resources that are for use there as revocable. And then finally, once all the tasks have stopped running on the machines, we can remove them from the cluster and do whatever maintenance that we actually want to do. Okay, so this comes up often when we talk about cluster management, but what about my persistent data? How do I run my stateful services on cluster managers? And so for that, we also introduced a concept recently that we call persistent volumes. So the idea behind persistent volumes is, again, that one of these frameworks through the programmatic API, so software can go in and can create a persistent volume for whatever task it's trying to run. Okay? And so it does that when it gets an allocation of resources through an offer. When it goes to launch any task, it can say, by the way, I also want you to create a persistent volume for this task on this machine. And of course, tell me about it in the future if the machine ever fails or my task fails or any of those other things happen. And again, we propagate the persistent volume information all the way down to the slave so it can record that information, and we can deal with all the failure scenarios that I talked about earlier. So what persistent volumes end up looking like on the individual machine is just like kind of dynamic reservations have preset out containers. We have these containers set up with things like volumes that are preset for those containers. So when a task goes to run, it can actually use any of the persistent volumes that have been allocated for it. But then, of course, if the task fails, then the persistent volume is going to stick around. And the next time that you try to run a task using that persistent volume, it'll still be there. So I think that the bigger picture of a lot of these features is that we're trying to build these things in specifically so we can run long-lived stateful frameworks. So not just all the stateless services that I really talked about earlier, the things we went after and attacked when we first started doing this at Twitter, but the stateful stuff as well. And really this combination of reservations, inverse offers, and persistent volumes really gives us the primitives to do something like that. Okay, so just a couple more slides, and then I'll take some questions. So these days, it's a pretty fun time. All of our other computers are effectively data centers. We can spin up data centers worth of resources very, very easily on any of the public clouds, or we just have them at our disposal at our existing organizations. And here by data center, I really just mean some collection of physical or virtual machines that we're grouping together and treating as one big data center computer. Because really the data center should just be another form factor. Just like our laptops are form factor, and the tablets are form factor, and the cell phones are form factors. And if Mesos is really this data center kernel that we're trying to build, the natural question is well, what's a data center operating system look like? And that's actually what we're doing at Mesosphere, is trying to build what we call the Mesosphere data center operating system. So to look at that stack, to look at everything that I talked about earlier in the presentation, what that ends up looking like is you've got this kernel-like layer that we call Mesos, and then you've got sort of this API layer on top, and then again you can either directly use something like Marathon to launch your apps or Kronos to launch your apps, or you can go and you can build your own scheduler and distributed system by using the Mesos SDK on top. And one of the nice things here is that when you end up building your software on top of this, you're abstracted away from if you're running on bare metal or if you're running on any of the clouds. And again, as I mentioned before, Marathon really, it ends up being sort of the init for the data center operating system. It's the thing that you use to launch your first tasks. And Kronos really ends up being sort of the cron for the data center operating system. Okay, one of the things we built when we were actually building this is open source, the DCOS CLI. So one of the first things that we actually built was a CLI, which is just for interacting with this data center computer. Obviously, data center operating systems need user interfaces. So the first thing we built is a CLI, and it's pretty cool. You can hook into it with any of the distributed systems you're trying to run on top, like something like Cassandra, and you can actually do something like DCOS package install Cassandra and actually get an implementation of Cassandra running up on the data center without having to actually touch anything, which is very, very cool. And at the same time, we've got some even tighter hooks in our CLI with certain applications, things like Spark as well. So if you want to run a Spark job, you don't even have to install Spark. You can just go ahead and do a DCOS Spark run to run Spark applications directly on your data center. Okay, so I've spoken for about 46 minutes. I'll stop now, and I'd love to take any questions. Yeah, so I'll repeat the question so everybody heard. So I talked about actually being able to do vertical scaling on an individual machine, and that obviously we can reach a peak of our resources. So you can't just arbitrarily take more resources on the machine. You have to actually schedule tasks inside of the container that you've actually launched for us to actually vertically scale up the container. So if all the resources are actually allocated to other containers or other tasks or other executors that are running, then they won't be allocatable, they won't be usable, so you won't actually be able to run anything inside that container. So the resources are accounted, so the TLDR is that the resources are accounted for in exactly the same way as if they were running outside the container. We just let you run the task inside and then scale up the container from there. Does that answer the question? I see. So the question is could you, if the resources are heterogeneous, which by the way is almost always the case, that there's a heterogeneous collection of, basic machine shapes. Can you? And so then the question is, can you? If you're running a machine, can you kind of like? So usually what ended up happening is if you're running a task on a machine and actually you wanted to vertically scale up, but you just could never fit on that individual machine, you'd have to shut the task down and then run the task on a different machine. Yeah. But if they're the resources available, then you can vertically scale up. And at the same time, once you've used those resources, you can vertically scale down. So the applications which end up taking advantage of this the most tend to be things like analytics, continuous integration things that are, compilers that are building things. Oftentimes, they're these shorter-lived applications that, could take advantage of the fact that you've already started doing some computation someplace. And so if you can just run some more stuff there right now, you're going to be able to do it far faster than if you were to bring up another one horizontally someplace else and then go from there. And so that's specifically why we built the things in. So things like Spark, for example, explicitly take advantage of this when it runs on Mesos. And when you go to run another task and Spark already has some of the data in memory on that particular machine, it'll run the task on that machine, it'll vertically scale up, it'll use the stuff in memory, and then when it's done, it'll vertically scale down, and then the resources are free again. And that saves you significant time in running your jobs than bringing it up someplace else. Other questions? Great question.
How do you prioritize different workloads on the same Mesos cluster? E.g., Spark jobs less prior than Marathon? Or perhaps also within the scheduler?
Yeah.
The single scheduler.
OK, great. So some of the slides I skipped in the rabbit hole part was specifically how we do the first level of allocation in Mesos. And that first level allocation is how we choose what resources to allocate to some of the different schedulers that are running on top. So the basic idea in the system is the first level scheduler, the default first level scheduler that we have is something that we call a dominant resource fairness. And it's a fair sharing algorithm, but it has weights. So you can actually attach weights to things like a Spark instance or Hadoop instance or Marathon or Kubernetes or whatever it is that you're trying to run to preferentially give those frameworks that are running more resources. So for example, you can, in fact, you can run 3 instances of something like Spark, and you can run one instance with a really, really high weight and the other ones with really, really low weights. And what that effectively enables is, the one with the high weight can kind of be your production one, which always gets the resources, and the one with the low weights can just be the ones that you throw away. So this is only part of it, though, because there can still be circumstances where things get scheduled in this fair sharing way that doesn't actually meet the needs of the organization. And that's specifically why we introduced the concept of reservations, is because reservations really lets an operator that's running the cluster be able to say to some part of its organization, I want to guarantee you're going to get at least 300 CPUs and 400 gigs of RAM, and so I'm going to put this reservation in place. Or I'm going to put this reservation in place, but you're going to fill it up dynamically based on when you actually run things. And effectively what that does is it just gives better guarantees than fair sharing with weights. So that's why we've introduced those other concepts. Yeah, and a lot of the things that have influenced these decisions have specifically been going and looking at the way our traditional host operating systems perform these same roles, and then introducing concepts that are amenable to the data center environment, to the distributed system environment, or in some cases are exactly the same.